Welcome. In this session, we'll find the solution of a network or solve a network problem using the Laplace transform approach. So let's suppose we have an example. Okay, so we'll say we have a network. There's a switch in the network. So we have a capacitor here and resistor here. Then we have a inductor and a resistor here. So this switch is opened at t equal to 0, and there's a voltage source here. This is 10 volts, and this is 4 ohm. This is 0.02 farad, and this is 3 ohm. This is 6 ohm, and this is 0.5 Henry. And our goal is to find I of t for t greater or equal to 0. So the problem is find I of t for t greater or equal to 0. That's what we have to do, right? And the method that we are going to follow is Laplace transform approach. As you can see, this is a second order circuit because this contains both a capacitor as well as inductor. So this is an example of a second order circuit. So we'll use Laplace transform. Before we use the Laplace transform approach, we must find the initial conditions or the initial value of the capacitor voltage and inductor current. So what we'll do, we'll draw the network just before the switching, means we'll redraw this network at t equal to 0 minus. As you can see, the switch is getting open at t equal to 0, means switch was closed before the switching action, it was closed. That means network is in steady state condition. What is the meaning of that? That means capacitor is fully charged and inductor is fully charged. When capacitor charge is fully, it acts as an open circuit and inductor acts as a short circuit. Okay. So we'll redraw this network at t equal to 0. So the network at t equal to 0 will be 0 minus, sorry. So at just before the switching, switch is closed. So there will be voltage source here. And capacitor will act as an open circuit. And inductor will act as a short circuit. So, and there is 6 ohm resistor here. So this is 6 ohm. This is 3 ohm. So this is the value of the capacitor voltage at t equal to 0 minus. And this is the current flowing, that is I of 0 minus. This is 4 ohm. This is 10 volts. Okay. So these are the quantities, right? So as you can see, there is open circuit here. There is no current will flow in this branch. That means V of 0 minus is simply the voltage across this 6 ohm resistor, right? So, and I of 0 minus is the current that is flowing from this, right? So this is I of 0. So we can write I of 0 minus simply as 10 divided by the total resistance 4 plus 6, that's equal to 10 divided by 10, that's equal to 1 ampere. Now same way we can write V of 0 minus, which is equal to 6 times I of 0 minus, because this is the current that's flowing through this resistor. So 6 multiplied by 1, that's equal to 6 volts. So we have found the value of the capacitor voltage at t equal to 0 minus and value of the capacitor voltage at t equal to 0 plus. All right. And inductor current at like this. So if we know the inductor current at t equal to 0 minus, we know the value of the inductor current at t equal to 0 plus, right? All right. So what we'll do, we'll redraw the circuit at for t greater than 0. So for t greater or equal to 0, what is happening here? Switch is getting open, right? So we'll redraw this circuit. So switch is now open for t greater than 0, and we have a voltage source here. We have a capacitor here. We have a resistor here. We have a inductor and resistor in series, and our goal is to find I of t for t greater than 0. Value of this capacitor is 0.02 farad. This is 3 ohm. This is 0.5 henries. This is 6 ohm, and this is open. So this is the equivalent circuit for t greater than 0. Now you can see there is no fun of this 10 volt in series with the 4 ohm resistor. So you can remove this. So what we'll do to find the value of I of t, we'll replace this circuit by this Laplace transform version. Since V of 0 minus, which is same as V of 0 plus, why? Because the capacitor voltage cannot change suddenly, which is equal to 6, and I of 0 minus, which is same as I of 0 plus, which is equal to 1 ampere. So the initial values are not equal to 0. So we have to replace the equivalent modulus of these capacitor and inductor for this. Okay, so to draw the equivalent model of this circuit, we have to use the modulus which has initial conditions for this capacitor and resistor. Okay, so we have seen the modulus of this inductor and capacitor in the previous classes. We know how to draw the model when with the initial conditions are, and one of the model that we have drawn, we say if we have a capacitor of capacitance C, and the initial value of this voltage is suppose V0, then we can draw the equivalent circuit of this capacitor as in the Laplace transform domain like this. This is 1 by SC, and sorry, SC, and this will be simply V0 by S. So this here V0 is simply 6 volts. All right, and same way we can draw the equivalent circuit of an inductor of inductance L, and if the value of I of 0 is I0, then we can draw the equivalent model of this inductor. There we can have two models, but this time we'll use the series model or the KCL model. Plus I of 0 divided by S and Ls. So what we'll do, we'll replace this circuit. This will draw the Laplace transform equivalent, and for capacitor we'll use this, and for inductor we'll use this. So drawing the equivalent model here. So since there is no fun of this part, so we'll not draw it. So we'll remove this part here. So we have a capacitor in series with a voltage source. Then there is a resistor, that 3 ohm resistor. All right. And then we have an inductor. So we will replace inductor by an impedance in series with the voltage source. Then there is 6 ohm resistor here. All right, so let me write the values now. This is plus minus V0 of V0 by S. V0 is 6, so it will be 6 by S. So it is 1 by SC. 1 by C is, I think, 0.02, that is 50. So 1 by SC will be 50 divided by S. And inductor is LS, so it will be S by 2, because L is 1 by 2 or 0.5. Then this is minus plus I0. I0 is 1, so it will be 1 by S. Then this is 3 ohm. This is 6 ohm. Not 2 ohm, this is 6 ohm. So this is 6 ohm. And here is the current that is flowing through this. So we'll write it as I of S. All right. Now you can write the KVL and get the value of I of S. So if we write KVL here for this model, if we write the KVL, so it will be current is flowing like this, right? So it will be 3 times I of S plus minus, it will, because we are encountering minus terminal. So it is minus 6 by s plus 50 by s times I of s plus s by 2 I of s minus 1 by s plus 6 I of s. This is equal to 0. So this is the KVL, right? Writing the KVL. Now arranging the terms, it will be 3is plus 6is is 9is. So it is 9is. I will take common. So it will be 9is. So is I will take common. So this is 50 by s plus s by 2. Here we have is. Then we have minus 6 by s minus 1 by s. That's equal to, it is 6 by s, s by 2. Sorry. Okay, 1 by s. All right. So this is okay. Have I done it correct? It is 6 by s. All right. So this is correct. Okay, I think I have written this wrong. Okay, this is not the model. It is Li naught. Okay, this is the model is Li naught. Okay, means we replace the inductor by Ls in series with a voltage source that has the voltage Li naught. Okay, so this is not 1 by s here. Sorry, this is not 1 by s here. This is simply L is 1 by 2 or 0.5. I naught is 1. So it will be 1 by 2. So this is 1 by 2 here. Sorry about this. So this is 1 by 2 here then, because the voltage source is 1 by 2. So this is 1 by 2 here. Then simplifying the terms a little bit. So it will be, if you cross multiply this, it will be 9 plus 100 plus s squared divided by 2s times is minus, if you cross multiply the terms here, it will be 12 minus s divided by 2s. This is equal to 0. So cross multiplying the terms again. So we will get 18s plus 100 plus s squared divided by 2s times I of s. This is equal, if I take it on the right hand side, it will be 12. Sorry, it will be 12 plus s divided by 2s. Now you can see 2s and 2s will get cancelled from this and this side. So is I can write simply as, so from this is simply 12 plus s divided by, first I will write s square plus 18s plus 100. Okay, dividing both sides by this s square plus 18s plus 100, we'll get this. All right, so this is our, so what we have here, we have is equal to 12 plus s square plus 18s. So what we'll do, we'll use partial fraction expansion. But to use partial fraction expansion, we must know what are the factors of this denominator term. So we must know what are the factors of this quadratic term here, right? So again, to write the partial fraction expansion, we must know the factors of this s square plus 18s, right? So if you compare it with the quadratic, this polynomial, so s square plus as plus, sorry, this is not the polynomial. So polynomial is a x square plus bx plus c 0. Then we know x will be equal to minus b plus minus under root of b square minus 4ac divided by 2a, right? And if the roots are alpha and beta, means if the two values of x are alpha and beta, then we can say ax square plus bx plus c can be written as x minus alpha into x minus beta, right? So in terms of factors, so what we have here, we have s square plus 18s plus 100, right? It's equal to 0. So that means s1 comma 2 means s1 and s2. What are the roots of this? So that is minus 18. If you compare it with this, plus minus 18 square minus 4 times 100. A is 1 divided by 2. So that is minus 18 plus minus. How much is this? 18 square, that is 324 minus 400 divided by 2. Okay, so that will be minus 18 plus minus. So 324 minus 400 is minus 76 divided by 2. So this will be equal to minus 18 plus minus 76 under root of minus 1. You know, under root of minus 1 can be written as j. So it is plus minus j times under root of 76. Under root of 76 is 8.72. Okay, so I have to please check. So S12 are this. So that means this will be 9 plus minus. You divide that by 2, 4.36j. Okay, so these are the two. Now you can see these are complex roots, of this. So that means we can write s square plus 18s plus 100. We can express it as s minus 9 minus 9. Okay, there is minus now. Okay, this is minus. Okay, I forgot the minus, so it will be plus 9 plus 4.36j and s, because what are s1 and s2 here? Minus 9 plus 4.36j. S2 is, okay, let me write minus term first. Minus, so S2 is minus 9 plus 4.36j. So it will be s minus s1. S1 is this, so it is minus is plus. Plus 9 plus 4.36. This is plus 9 minus 4.36j. Okay, so this is the quadratic polynomial. Okay, so now we can use the partial fraction expansion. That means I of s. So we have I of s, which is equal to s plus, what was this? S plus 12 or 12 plus s divided by s plus 9. Okay, let me write the original polynomial first. So it is s square plus 18s plus 100. That I can write as now s plus 12 divided by s plus 9 plus 4.36j, s plus 9 minus 4.36j. Okay, so this we can write as a partial fraction. So it will be a1 divided by s plus 9 plus 4.36j plus a2 divided by s plus 9 minus 4.36j, right? So our goal is to find now a1 and a2. How do we do that? By multiplying both sides by this denominator term. S plus 9 minus 4.36. So multiplying both sides by this denominator term. Both sides by s plus 9 plus 4.36j, s plus 9 minus 4.36j. We get, so once you do that, from the numerator and denominator side, this term will get cancelled with this term, right? So we will be left with s plus 12. That will be equal to a1 s plus 9 minus 4.36j, right? Because this term will get cancelled once you multiply it by this term. A2 s plus 9 plus 4.36j. All right. So to find the value of a1, what we'll do, we'll make this term equal to 0. How do we do that? If we put s equal to minus 6 minus 4.36j, a2 will be equal, a2 term will be equal to 0, which contains a2 here. So it is put s equal to this. So we'll get minus 9 minus 4.36j plus 12 is equal to a2 minus 9 minus 4.36j plus 9 minus 4.369j. So from this, what we'll get? So it will be 3 minus 4.36j, which is equal, because minus 9 plus 12 is plus 3. A2 minus 9 and plus 9 will get cancelled. So we'll be left with minus 8.72j. 8.72j. Please check the calculation one more time yourself. So that means a2 will be equal to 3 minus 4.36j divided by minus 8.72j. All right, so once you divide 3 by 8 point, this If we divide 3 divided by 8.72, it is 0.3334. This j, right? But j is in the denominator, so it will become plus. So this term will be plus, so it will be 0.344 j, right? So once you divide it by this, once you divide 3 by this, and this one will be j and j will get cancelled, it will be 0.5. So you can write it as 0.5 plus 0.344 j, right? So this is a, sorry, this is A1, not A2. This is A1, okay? We have put it wrong, so this is A1. This is the value of A1. Now to get A2, what we'll do? To get A2, we'll put S equal to -9 plus 4.36 j. Once you do that, you can see this term will be 0 now. Okay, this term will be 0. And the A1 term will be 0. So it will be -9 plus 4.36 j plus 12. This is equal to 0 plus A2. And this is -9 plus 4.36 j. Then we have what we have here. Okay, I hope I'm done correct. And then we have 9 plus 4.36 j plus 9 plus 4.36 j. So simplifying this, so we can write it as 3 plus 4.36 j. This is equal to A2 minus 9 plus 9 will get cancelled, so it will be again 8.72 j. So A2 will be simply 3 plus 4.36 j divided by 8.72 j. So dividing the denominator by this, so it will be 3 divided by 8.72 j plus 4.36 j divided by 8.72 j. You can see there is in the denominator we have j. When it comes to the numerator side, it will be minus. So it is 0.344 minus j. So it will be minus. This will be simply 0.5. So you can write it as 0.5 real part minus the imaginary part. So minus 0.344. So A1 is equal to 0.5 plus 0.344 j. A2 is equal to 0.5 minus 0.344. You can check A1 and A2 are complex conjugates of each other, right? One has minus j term, other has plus j term, right? So substituting back here, we'll get I of s as a partial fraction. So I of s will be equal to 0.5 plus 0.344 j divided by s plus what we have here, s plus 9 plus 4.36 j. 9 plus 4.36 j. Then we have A2 is 0.5 minus 0.344 j divided by s plus 9 minus 4.36 j. Now we have this in the form of s plus a, so we can write it as the inverse Laplace transform of e to the power of minus at ut. Only difference is a is complex number. That's the only difference here. Okay, a is a complex quantity here. So if we replace it by its inverse Laplace transform, we'll get I of t will be equal to 0.5 plus 0.344 j e to the power of minus 9 plus 4.36 j t, right? U of t plus 0.5 minus 0.344 j. This is the coefficient or the residue e to the power of minus 9 minus 4.36 j t u of t. Now you can see in the one term we have e to the power of minus 9t. In this term we have e to the power of minus 9t. So taking it out and taking also u of t out from this expression, so we'll get I of t will be equal to e to the power of 9t. I will take common, so So it will be 0.5 plus 0.344j. We'll be left with e to the power of minus 4.36j t plus 0.5 minus 0.344 j e to the power of plus 4.36j, because minus minus will be plus t, and outside is u of t. So taking e to the power of minus 9t and u of t out from this. So now we will arrange the terms a little bit. In other words, writing it in terms of cosine and sinus. That's the goal here. Okay, so from here we have 0.5, here we have 0.5. So it will be 0.5 e to the power of, so this is minus, this is plus. So I will write the plus term first. I will write this term first, 36j t minus, sorry, this is plus. Yes, so it is e to the power of minus 4.36j. So I wrote this term first, this term. Okay, then I wrote this one plus. Now taking this common, 0.344j, 0.344j. So it is 0.344j. It is equal to e to the power of minus 4.36j t. Let me write j in the front side, so to avoid the confusion. So it is t here, j I wrote on the front side. So it is plus 4.36 j I will write here plus t to y. Okay, so u of t. All right. So now we'll arrange the terms. So if I multiply this, the numerator and denominator by 2, what will be left? 0.25 multiplied by 2 is 1. So it will be simply 3.6 j I will write here plus e to the power of minus 4.36 j I will write here divided by 2 plus, if I multiply and divide by 2j, so we'll multiply and divide by 2j. So what will happen here? It is 2, so 0.344 multiplied by 2 is 0.688. Okay, j and j is minus j, so that minus j is minus 1. So I will take that inside. So it will be 0.688, right? J and j will cancel, or it will be simply minus 1. Minus 1 I will take inside. So it will be e to the power of for j 4.36 plus t and minus e to the power of minus j 4.36 t, right? So it will be here j and j is j square. Here we have a j and j here. So if we multiply by j and j, that is j square. J square is minus 1, and that minus 1 I take inside. So we are left on now. You can check this. This is e to the power of j theta, e to the power of minus j theta divided by 2. That is cos theta. It is e to the power of j theta minus e to the power of minus j theta divided by 2j. That is sine theta. So we can write it as 90 cos of 4.36t plus 0.688 sine 4.36t, and outside we have u of t. This is the current. Okay, this is the current in this. So what we did, actually, we found the current when we opened the switch in the second order circuit using the Laplace transform approach, Laplace and inverse Laplace transform approach. What we did, we replaced the circuit after we did the closing after we did this switching, we replaced the network by this equivalent Laplace transform version. We got the solution like this. So this is the solution here. So we got the current that's equal to this. So this is how we find the current, and when the roots are complex here, when the roots of the quadratic term are complex here. All right, I hope you have got the meaning from this, how to solve when the roots are complex. This is very, very important case, very important case. Okay, now I will solve the same problem in the next session without doing this thing. Okay, without solving it, but getting the answer from initial conditions without doing this complex quantity involving these complex quantities. All right, So without doing this, I will write the solution in the next session. All right. So see you in the next session.